topic. Moving on. Imagine that you have two groups and and you want to see whether or not their means are significantly different from each other. In other words, can you be 95% sure that these two groups are really different? That the control group and the experimental group actually had different results? If you want to be 95% sure about that, just as you've seen us before, we're going to have to apply a formula with some kind of standard, as in the t-scores, right? So we're going to be doing a series of what we call t-tests. And before I can get to them, I want to give you general ideas about hypothesis testing. If I don't do this, Chris Terry will be really confused when you get to him next for experimental. And we don't want to do that to him. He's got enough work to do. So I'm going to introduce the topic of hypothesis testing, the types of ways that we can make errors when we do it, because don't forget, samples aren't the same as populations, and we can get the answers wrong sometimes. Then going from the topic of hypothesis testing as a general idea and the steps that we go through, then we'll start doing in a particular order from easiest to hardest, the three types of t-tests. Okay, so why do we have to do hypothesis testing mathematically? Why do we need this? We need this because we get it wrong a lot if we don't. We're terrible at guessing whether something is by chance or whether there really is a difference that we could rely on, that we should, bet the farm on, that we can dose people's medications by. And the reason why we're bad at guessing is because we tend to see patterns in random stuff. We build in the idea of patterns into many belief systems that we have. Think about constellations in the sky. Right? So constellations in the sky are interesting because they actually weren't put there to look like whatever, a W, a Big Dipper, whatever the other ones are. I don't even know. Nobody went and placed them like that so that we would have these constellation beliefs. If you believe in God, then you probably believe they were placed like that, maybe, given certain beliefs in a supreme being. But even if you believe that, if you go to another culture, they have different names for the same star clusters. Or whole clusters that we see really strongly, they might not even have noticed. And there's other clusters that they think have really obvious pictures in them and names. One of the ways that we can see this, we don't even have to go as far as the stars, has to do with the moon. We talk about the man and the moon, and some of us, when we look up at the moon, we can see how that happens. We can see where the eyes would be, where the nose would be, sort of, where the mouth would be, sort of. Like, it doesn't look like somebody drew a man in the moon, but you can see the man in the moon, right? We kind of like fill in the gaps and we see the man in the moon. In Japan, the idea of the man in the moon is not their cultural thing. They see a rabbit in the moon. A rabbit. And they don't understand where this man picture is. And when you try to show it to them, they're like, that's really stretching it. Like, that's not what you merely made that up. That's not good. And that when they show us the rabbit, those of us who've been raised in this culture, we look at that and go, there's nothing remotely like a rabbit when I look at the face of this moon. If it were, I would have seen it by now. No, you wouldn't, because you think it's a man's face. The rabbit in the moon, once you've been exposed to this idea, is not hard to see at all. We are really good at seeing patterns when there aren't any. So it's important for us to find another way besides guessing and using our intuition and using our cultural beliefs. It's important for us to find some other way to test our ideas. some of our ideas. And the ones that can be tested quantitatively, especially, we use hypothesis testing for the scientific practice of hypothesis testing. So this is where science intersects with culture, is when it's something that we want to be precise about and we think that people are somehow biased when they're guessing the answer, um, by our culture typically, or desires typically, then we use statistics to try to get to what we think of as the truth. Now, if you've taken courses in postmodernism, you're like, but there isn't any truth, and it's okay if you see the rabbit in the moon, then that if you see it, it's there. And yeah, that's all. We're going to call that philosophy, and we're going to put it aside. Okay, this is the scientific method doesn't go well with every other belief system, but it goes well with some of them. Psychology is science. And so we use the scientific method to find out things about people that we can then use to understand them and predict and control and everything else that you do with science, but also to design counseling methods, behavioral schools, all sorts of things. But we need to know that what we're doing is likely to work, right? So if you have a certain type of counseling method that you think helps people, before you package it and advertise it, you want to test it. And that's what this is for. All right, so when we do this hypothesis testing, what we're trying to do is determine whether something called the null, N-U-L-L hypothesis is right or wrong. And the null hypothesis is the hypothesis that nothing's happening, that there's no difference between a control group and an experimental group, that the medication didn't work, that there's no difference in the IQ between men and women, whatever it is that you're trying to find out. The null hypothesis is that it's not happening. We put it out there to test. It's like we're testing the devil's advocate. It's not usually what we want to have be right. If you've been designing a therapy method, you would like there to be a difference between the people who didn't get the method and the people who did in terms of the results. You want there to be a difference. If you design a med for depression, you'd like that med to work. You want to see a difference between different dosage levels. There are times, however, when what we want is for there not to be a difference. I used to do a lot of studies on the difference between men and women in fill in the blank, helping behaviors, aggression scores, adherence to sexual stereotypes, all of that stuff. And what I was often trying to demonstrate was that there was no difference between them, not when you looked at science, with science. So sometimes we like the null hypothesis and sometimes we don't. Most often we don't. Most often we're hoping that an alternate hypothesis, and that's an official words here, alternate hypothesis. The alternate hypothesis is what we are saying when we say the medication will work. There will be a difference between group A and group B. The experimental group showed a difference from the control group in how they responded to talk therapy. So usually we care most about the alternate hypothesis, but we have to actually test the null hypothesis. And here's why. It has to do with what I call noise, and that's shorthand for confounding variables. So let's say that you found a difference between the control group and the group that got your treatment of something. It could be that they are different because of what you did, but it could be that something else happened. It could be that it was a better day the day you tested them. It was nicer, it was brighter outside, the weather was great, or it was a holiday, or the day that we found out that we were going to get another stimulus check and you're checking mood, right? So it could be that something else is affecting the results. So we can't say with certainty ever that what we did worked. We just know that there's a difference in the scores, but we're not always really sure about why. We hope we know the reason why. That's why we do repetition. That's why we test things over and over again. We're looking for reliability. But we can test the null hypothesis. We can test whether or not the difference occurred. We can say, okay, the null hypothesis, the one that says nothing occurred here, is absolutely right or wrong. Nothing occurred or something occurred. We don't have to know the reason. We don't have to be sure about the reason why when we test the null hypothesis. That's like an on-off switch, yes or no. It's much less complicated than the alternate hypothesis. It's easier to write, it's easier to think about. Nothing worked, the med doesn't work. I thought I knew the difference between these two groups. They're not. Men and women's scores on whatever test aren't any different than they were, even though my sexist brain thought they would be. Or better yet, my feminist brain thought they would be, and I thought women had more empathy than men, and I do this test and nope, they don't. Like that kind of thing. Actually, women typically do. If you're talking in general. However, male psych majors don't differ from women in terms of empathy levels. That's encouraging since they're going to go out to help people in general. So that's a good thing. Okay, so in order to test the null hypothesis, we can't ever be entirely sure. We can't be entirely sure about our results because we have a sample instead of a population. And we've already had this conversation. Samples are not populations, they're just a subset of the population, and they may not actually represent the entire population. They're the best predictor we have, but it may not be good enough. So, hey, Isaac, your screen is like flashing bright, dark, bright, dark. Is there something you could do about that? It's driving me nuts. Thank you. Oh, he froze. Oh, he's gone. Okay, so so if I were to ask you when you think it is, when something is true, we're all going to have, thanks, Isaac, we're all going to have different answers. So like, I have this way to flip dice in this little plastic cup that's theoretically magic, but it's actually just physics. It's the way the cup is shaped. And there's a little die in there. And if you just shake it once, you can predict what it's going to be on top by how it was just before you flipped it. So you have a cup, and the cup is a die, and put the cover on it. But before you put the cover on it, you look at the side of the die, and you can see the number that's going to come up next time if you just go like this to shake it. So I've done this with little kids. I've actually pulled this off with freshmen too. And I say, tell me when you think that it's that I'm magical, like I can actually predict the future. Tell me when you keep your hand up as long as you think that's true. And I've had students and little kids especially just keep their hand up the whole time. Like, of course you can see the future. We're watching you, you're seeing the future. But once I get to college students, and probably if I did it with high school kids, but I did it with like 4-year-olds. So with college students, they all start out with their hands up because they're like, what the hell, how did you do that? And then bit by bit, most of the class's hand goes down, but not all at the same time. Some people, it just takes one. Some people, it takes 3 or 4. I had one student, a college freshman, I hit 10 times doing it before the student said, okay, this is a trick. Nobody, you can't read the future like this. Everybody has a different kind of tweak point at which they will say, okay, something's real or something's not real. And because everybody has a slightly different spot where we would agree or disagree with stuff like that, we have to have a cultural norm that we can apply. And that's where that whole 95% and 99% sure stuff comes in. Remember the confidence interval 95? That meant we were 95% sure. The population mean was between these two numbers. Or we could be 99% sure, we had a bigger range of numbers, right? So we call that an alpha level. how sure we want to be, we call an alpha level. You'll learn a little bit more about this as we go. And that alpha level, in our psych experiments that we're going to be practicing with, and what most psychologists use for their how sure do we want to be, is either 95 or 99% sure. We have the numbers to test for other levels. We have t-tables that can do that, but in fact I put one up on Canvas now, but a different one. So there's a better t-table that can do what we're going to need it to do. So we have to have that alpha level so that we can all be in agreement on how sure we want to be about things. All right, hold on. Let me just look at these notes for a second. I have examples I don't need because we already talked about some stuff. My notes are slightly out of order with how I'm talking, so just give me a second to. They're on paper, believe it or not. Okay, so let me just review this idea. Let's say that you have a therapy method that you want to test, and you set up ahead of time what your alpha level is going to be for this experiment that you're going to use to test it. You want to be 95% sure that your method works. And to test it, we actually are going to test the null hypothesis, but we're going to come up with both hypotheses. So the null hypothesis, the one of nothing happening here, will say there's no difference in the depression scores of people who had the therapy method and people who didn't. Okay, so the independent variable will be whether or not you had the treatment, and the dependent will be your depression score. And the null hypothesis will say there's no difference between the scores of the control group who didn't have the method and the experimental group that did. The alternate hypothesis will be either the scores will be different because maybe you increase people's depression, or you could state it as the scores will be less, because that's what you're really shooting for. We talk about those two different ways to predict as two-tailed versus one-tailed, and I'm going to be going over that quite a bit, so don't worry if you don't remember these words right now. Hold on, I'm going to close the door for sound purposes. Hi, honey, welcome home. Hey. Okay, Gertie, let's go back to class. Okay. You guys smiling at yourselves, or are you smiling at the fact that I have a life? A little of this. Yeah, I know. It's always funny when you see a teacher actually has a room, a life, a house, a garden out back, a dog. Yesterday, I was in an official meeting where we were making major decisions, and suddenly everybody's got cats on their lap. It was hard to concentrate. It's like, you guys probably know Kelsey. It's like Major Kelsey. She has a cat where she's living right now, and it's just much more fun to watch the cat than Kelsey, I have to say. That's probably a good thing for a teacher too. All right, so when we say that we're going to reject that null hypothesis based on the math that we're going to learn how to do, we could be right and we could be wrong. We want to be 95% sure we're correct, but we can be wrong. And when we're wrong, there's actually two ways to be wrong. And there's two ways to be right. And I am going to now switch to share my screen and show you what I mean, because I'm going to put this in the form of a table. And then it will be in your notes. Anyway, the example that I'm going to use here is not the therapy example. It's instead the example of when a jury makes a decision. There's two ways to be right and there's two ways to be wrong, and it's an easy example to follow. And then I'll do it again with the does the therapy work. So hang on while I get this together. Okay. Share my screen. Okay. Okay, so I'll show you what a decision table looks like. This is just to be able to talk about it. We don't actually use this when we're making decisions. We have a more clear method, but is a person guilty of a crime? The null hypothesis, we write like this: H for hypothesis, and then a small letter 0. Null just means 0. None, it means nothing. None, 0. The null hypothesis is that the person is not guilty. Nothing happened. And that's what we're going to test. By the way, the alternate hypothesis, just so you know it, could be that the person is guilty. Okay, now, did I forget the letter? Did. Okay. So here's the way that the decision making happens. Hold on, I've got a table with. Okay, so the decision is that we're either going to hang on to that null hypothesis. So that's called accepting, for now at least, the null hypothesis, or retaining is the language that I learned how to use, and say not guilty. Or we're going to reject the null hypothesis and say guilty. All right, so basically up here where I put decision, I'm just going to say decision about the null hypothesis, just to make sure you can see that. Apologize for this terrible handwriting. Okay, so that's what this column is telling us about. And each row of accept and reject, two things can happen. So in these two columns, it's going to be about truth. What's really true? Did they or did they not commit the crime? Are they or are they not guilty? So let's say that the truth is that they're not guilty. Not guilty in that column. And in this column, the truth is that they're guilty. Why do I keep forgetting that letter L? Okay, so there's 4 things that can be happening here. There's the truth, and there's the jury's decision. And when you have 2 ways that it can be true or false, that's 2, and you have the jury's decision deciding it's true, deciding it's false, then that is a 2-by-2 decision table. So, for example, if we say that the person is not guilty, we accept the null hypothesis, and the truth is that they're not guilty, that's this square here, and we call that a correct decision. The other way we can be correct is to say that they're guilty, this bottom row, and they actually, in truth, are guilty of the crime. That's also a correct decision. Now you can see that there's 2 ways to get it wrong. So if we, I'm going to go down this not guilty column. If they're not guilty, but we say they're guilty, we've made a mistake. We call it an error in hypothesis testing. And in fact, we call this one a type 1, or also known as alpha, which is written like this, error. A type 1 or an alpha error. And notice that symbol, because sometimes that's all you see. It's just that little symbol. Often when you're doing hypothesis testing for a class, like a textbook or something, or online questions, you'll see this. That means that you're looking at the alpha level 0.05 in a t-table. That tells you what column you're going to be using. Okay. I'm going to erase that part because it's just going to confuse you later why that's up there. Okay. So the other way that we can be wrong is if the person's guilty of the crime, but the jury decides that they're not guilty. That's also an error, and it's called a type 2. These are Roman numerals, right? Also known as beta error. Okay, that's the logic of testing the null hypothesis. There's 2 ways to be right, and there's 2 ways to be wrong. Just quick reviewing. You could be right if you hold on to the null hypothesis and decide nothing's happening, the person's not guilty in this case, and they're actually not guilty. The other way to be right is if you say they're guilty, you make the decision that they're guilty, and they actually in reality were guilty. There's 2 ways to get it wrong. One is if we reject the null hypothesis that says not guilty, and we say they're guilty. We're rejecting the not guilty idea. We're saying they're guilty. Something did go on. And that's an alpha error. That turns out to be extremely important in hypothesis testing. It's how you find your t-value, for example. And then the other way to be making an error is to say, all right, I think that the null hypothesis is correct, that nothing actually was happening, the person's not guilty, but they were guilty. Now you can imagine, depending on the crime, there are different consequences for this. If you say that a mass murderer is not guilty and you get it wrong, that's a problem. So if you do that, then the beta error is a big deal problem. But if it's petty theft or third time with pot in your pocket, that the results of being wrong matter more if you say that they're guilty. If you're in a state like New York where there's a 3 strikes rule, right? Where there was, at least. There's a state, I don't remember which one, it was just in the news this weekend, where a guy was discovered with pot 3 times and ended up with a life sentence. For real. They didn't get him out until he had already served 20 years for a personal use amount of pot. So deciding that they're not guilty doesn't have big social consequences. Nobody's lives being put at risk. It's not as big a deal. And that's an alpha error. And most crimes, that's the error we would prefer juries made. Saying somebody's guilty when it's a capital crime and they weren't guilty, that's a tragedy, right? Okay, so let me apply this now to the therapy idea. Let's say that you have a null hypothesis of I'm not going to change this table. I'm just going to, because it's just going to make a mess. I have so many places where it says, well, no, you know what? I will. I'll let me just replicate it. Okay. No, I'm going to erase. I changed my mind. Sorry. So not guilty becomes therapy didn't work. Guilty becomes it did. Doesn't work. Doesn't work means doesn't change somebody's depression score. Or it doesn't make it lower, at least. Doesn't work or it works. And then instead of saying not guilty or guilty, we're going to say doesn't work and works. And then going up here where I wrote out the hypotheses and with not a lot of words, I'm going to do that again. So what we're looking at is difference in scores on a depression inventory after therapy or after not having therapy. Okay, so what we're saying in the null hypothesis is no difference in the scores. That's what we mean by doesn't work. So the null hypothesis would either be doesn't work, you could write it like that, or you could write out no score differences. In other words, the means are really close to each other. And when we run it through this mathematical formula, we find out there's no real difference. And the alternate hypothesis, the one you really care about, is that the scores are lower. But say this is a brand new method that nobody's tried before, and maybe it screws things up even worse. So let's just say somehow it works to make a difference, and the scores will be different. Have you noticed that when I write, my hand gets ahead of my spelling, and I have to constantly go back and fill in the letters? It's constant. This is why I'm usually happy not to be writing for a class. Okay, so let's take a look at this now. The truth is that it either works or it doesn't, and our decision about the null hypothesis, the one that says it doesn't work, is either we're going to accept it and say it works, or we're going to reject it. I mean, it doesn't work, and then or we're going to reject it and say it works. There's two ways to be right, and there's two ways to be wrong. If the therapy doesn't work and we said it doesn't work, we're correct. If the therapy actually works and we decided through this big mathematical process that it works, we're correct. There's two ways to be wrong. If it doesn't work, but we think it works, after our big mathematical formula stuff, then we've made an error, and that's known as an alpha error. And if the therapy method works, but we decided it doesn't work because of our big mathematical thing, then that's a beta error. Now, I want to talk to you a little bit about alpha error. This one right over here. Okay. Alpha error is when we reject the null hypothesis. The null hypothesis says nothing's going on, and we say there is a significant difference between the control group and the group that got the therapy. The scores are different, significantly different. We ran it through our little mathematical formula, and we find that there is a significant difference. When we do that and we're wrong, it's called a type 1 error. It's also called an alpha error, and we preset alpha error. We build it into the formula we use so that we have accounted for it ahead of time. That's just the way the process was developed by somebody back in, like, I don't know, the 1940s or something, 50s, something like that. This is a method that's been around a long time in hypothesis testing, in other words. And there are many ways that you could have developed this, but that person decided it was easier to preset and to input the alpha level as either part of the mathematical problem or compare our answer that we get when we run this mathematical formula to a table with t values in it. That's a method we're going to use, and don't worry if you didn't get that, because you're going to have many chances to learn it. We preset alpha, and what we preset alpha at is either 0.05 or alpha at 0.01. Now I want to talk to you briefly about the difference between those two and consequences. When we say that we want to be 95% sure, that actually has consequences. If we decided we want to be 95% sure rather than 99% sure, and vice versa. There are some things that we need to be 99% sure about, and there are others that we don't. Let's say that somebody figures out a medication that they think will reduce the worst of the COVID symptoms, for those who are at most threat, on ventilators, that kind of thing. They think they have a medication that will help. They test it with a sample. Now, do they want to be 95% sure that it helps? Well, maybe, because anything that we can do to help is good. So even if we're only 95% sure, that's not bad. Why don't we want to be 100% sure? Because we can't, because we're using a sample. So we preset how sure we want to be, and you could choose 95 or 99, 0.05 or 0.01 errors. Now, let's say that the side effects of this medication are minimal, nothing, no biggie. Person's nose turns blue, the end. Okay, I'd be happy if it was 95% sure that it works. That's a good risk to take. If the only consequence is that their nose turns blue and it turns back again 2 weeks later, no problem. 95% sure is good enough to try it. I sound like President Trump, don't I? Try the med. Drink the bleach. Maybe we can clean the person from the inside out. How about that? What happens if you drink that stuff? But what if the consequences, the side effects rather, were that it might cause heart attacks or strokes or seizures or change your T cell count so that you're susceptible to HIV? Consequences. Those side effects are not nothing. Those side effects are a big deal. How sure do I want to be that my medication works? I would like to be pretty damn sure. In other words, I'd like to be 99% sure, because it's not a good idea to give it to people if you are pretty damn sure it works, if in fact it's going to have side effects of heart attacks, seizures, strokes, lower T cell counts. I want to be really sure, and I can't be 100% sure because I can only test it on a sample, but I can be 99% sure. I can limit myself so that I'm 99% sure before I say it works. Making sense? It's very philosophical. Logic. This is the part where when I said the course is half logic and half math, we're heavy into the logic. All of these ideas you're going to need to apply to what we're doing going forward. Okay, now I'm going to fine tune this a little bit, and I'm going to say, I can decide whether I want to test, let's say this therapy method, we'll use that example again. I can decide whether I want to test whether or not it just changes the depression scores compared to the control group, or whether I want to be sure that what I'm testing is that it decreases depression scores, or that it increases happiness scores or something. I can choose which direction I want to focus on, or I can choose that I want to focus on either direction, any change. This decision we refer to as the tails that we're going to test with. And this is going to, you need this information to use a t-table. You may have noticed at the top of the t-table we used, if you saw it, that it said it was a two-tailed t-table, appropriate for using confidence intervals. Here's what that meant. Remember, there was this mean in the middle, and then we were trying to find the confidence interval, whatever score this was and whatever score this was, because we wanted the middle 95%. You remember that? So what we care about then is, what are the values that when we add it to the mean and subtract it from the mean, that's going to give us that middle 95%, which means we want to get rid of some of it over here and this one over here. These are called the tails of the distribution. And notice that when we try to get the middle group, we're talking about two tails. Now, Imagine this curve is actually about the depression scores. Okay. And the vertical axis is the number of people, the frequency of people who get the various scores. It's a normal curve just because I want it to be for this example. And if we were going to do a two-tailed test, it would look like that picture. So two-tailed means we're looking just to see if the scores are different. If this is the depression score of the control group, say, then I would be looking to see whether my group's scores were way over here in this tail on the right, or were they way over here in this tail on the left. Another way to look at this, and most students really hate this way, but I think it's really useful. Let's say that's the control group, and this blue group that I'm about to put up is the experimental group. And what I care about is really if their scores are lower or higher as a difference. In the end, they're going to be lower or they're going to be higher, right? In reality, the scores are either going to be the same, or we'll find out which direction they are once we give the score, once we give the scale. So in the end, the blue group could look, sorry about that, could look a lot like this group here, or it could instead have, let's say I screwed it up and I had higher scores come out, or it could look like this group over here. Or let's say that I actually got a great therapy method, and sorry, I didn't make this scale wide enough here. It could look more like this group over here, where they're down at the low end of the score for depression. That's what I'm really hoping for. But because I don't know yet whether my method works, it's brand new, I made it up. What I'm really looking for when I do a two-tail test, when I set alpha level based on 0.05, and then I decide I wanted to see if there's a difference higher or lower, I'm doing what's called the two-tailed test. It's going to give us a different t-value, which is going to change the final answer. So I'm looking for a mean for the group that's either higher or it's lower. But, okay, now this is where you're not going to like this at all. So when I say I want to be 95% sure, that means that I'm willing to be wrong 5% of the time. And if I do a two-tailed test, that puts 2.5% of the curve over here and 2.5% of the curve over into this end, this tail. You get that? Okay, if instead I do a one-tail test, let's say I'm predicting, sorry, I don't want to keep making new curves. It'll be, it'll suck. Okay, let's say that instead I want to do a one-tailed test. I'm going to actually put it in red so you really can see. Okay, if I want to do 1% one-tailed test and I still want my alpha to be 0.05, then that means that this top section over here, and I'm predicting my depression scores will be lower. That means that everything off over here to this right, this group over here is not, we don't care anymore. We're predicting that their scores, that the scores from the experimental group will be lower. We're only looking at this part down here on the left, the low scores. Sorry. Okay, so if that's what I care about, then down over here, actually, it's gotten bigger. And that's 5% of the curve is over there. notice my score got a little closer to the hypothetical mean. And this turns out to be like this down here. And if my mean score could be a little bit closer, then that actually gives statistical power to my formula. A statistical power means that that the method I'm using to test the hypothesis has enough mathematical power to find a difference. And sometimes all we care about is in one direction. We use that one-tailed hypothesis in order to keep as much power in the mathematical formula as we can keep. It changes the t-value we have to use in the formula. And that makes it easier to find if there's a statistical difference between the groups. If we have to use both tails, it weakens the formula a little bit, it weakens the result. And the mean has to be a little further away from the other group to find a statistical difference. This all probably went way over most of your heads. But you have it in notes in case you have to refer to it. Now you have it in the audio and video. Okay. All right, so what time is it? Gotcha. What I want to do next is talk to you about the type of tests that we're going to be doing next. And those are 3 different types of t-tests. And I believe that we don't need me to share my screen for a little while. And then most of the rest of the course is going to be me sharing my screen. Hang on, I'm getting there. I'm getting there. I think I need this. There it is. I actually found an excerpt from a stats book that in like a few sentences does what I used to take half an hour to explain. Okay, so we're going to do 3 different types of t-tests. I'm going to tell you about them in the order that we'll be doing them. T-tests are always looking at the difference between 2 means to see if there is a statistically significant difference. And the word significance just means, is it statistically different? So is there a statistically significant difference between the 2 means? It can only do 2, it can't do more. But there are different situations in which we're going to compare 2 means. And those different situations each get a slightly different t-test. Mathematically, it's quite different. The process of going through the hypothesis testing, there's a stepwise process. You're going to learn it and you're going to apply it for all the t-tests, and you're actually going to apply that method for doing correlation as well. The only thing that really changes in the big way are the types of hypotheses we make and the math. Okay, but the process goes like this. You set a null hypothesis and an alternate hypothesis and an alpha level. You go through some math and you get what we call a t-score. And then we compare that t-score, we call it t-computed. We compare that to a t-score in a table, and then we make a decision about whether or not to reject the null hypothesis, whether or not to say, nope, nothing's going on here. There's no difference between these means, or no significant difference. It's due to chance. I'm 95% sure. Or I'm 95% sure that this difference I'm seeing is real. Okay. How willing am I to be wrong? 0.05. If you look at that table I put up earlier, that's the little bottom left box with alpha error in it. We preset it. Okay, so what situations do we do? What do we come up with when we're trying to do a t-test? There's 3 different math formulas that we're going to be applying. They're all basically what they're looking at is, are the means far enough apart so that we can say the groups are different from each other? Or instead, are they a little bit too close to each other and we can't really reject it? The null hypothesis. All right, so the first situation is when we have a known population, like the one that I used earlier for z-scores, right, was IQ. We have a known population mean. Mean was 100. And we have one sample. And we just want to see whether that sample is significantly different from the population. And by significantly different, all we mean is we can be 95% sure that when we say it's different, it is. Significantly doesn't mean important, doesn't mean amazing. It just means we can be 95% sure we're correct, or 99. So this is called a one sample t-test. Again, a one sample t-test is when we're comparing the mean of one variable in one sample to a known population mean. Let's say that I'm the governor of Massachusetts and I want to say that our graduating high school seniors are smarter than anybody else's. My state's the best, you should move here. Can get the average SAT score from graduating seniors all around the country. The College Board would be happy to give you that number. And then you can do a one sample t-test to compare the Massachusetts scores to the known national population mean. Okay? Isaac, you hate this stuff, I can tell. When we get into the math, it'll at least give you something to do. It'll pick up a little bit. Okay, that's a one sample t-test. The next kind of t-test is when we have two samples. They're different, they're distinct, you can't be in both. You're in one or the other. Think of the old versions of gender, right? Men versus women. I'm going to be using examples with men and women a lot because my other area of interest is gender, the old style. So, I mean, it's old stuff. I don't do it anymore because I don't actually like new definitions of gender. So I gave up on that whole area. But I use that one a lot. Or you can look at people who got the method of therapy versus people who did not. Okay, so that's called an independent t-test. You have two independent samples. Independent just means you can't be in both. College seniors versus college freshmen on how much they like the school. College seniors versus college freshmen on how confident they are that they picked the correct major. That's a terrible one to ask anybody, especially during a pandemic. Everybody's like, I don't know what the hell I'm doing. Freshmen don't know because they don't know yet, and the seniors are going, oh, no, what job market, right? So that's an independent one. And then the next one has many names. It's called a dependent t-test, and it's called a paired samples t-test. I'll just give you those names. There's others. But in this case, you only have one sample, but you're testing them twice. So you're getting two means from the same sample. Think about the whole pre-test, post-test design. We can get a group's depression scores, we can put them through our therapy method, and then we can check their depression scores afterwards. One sample, but you're measuring them twice. That's one of the reasons why we do this dependent or paired samples. I participated as a research consultant after the fact. This happens to lots of psychologists. Somebody designs a bad study, they perform it, they have their numbers, and then they ask you to sign on to the article and do the math for them. But they asked the wrong stuff at the wrong way at the wrong time. And I ended up with this study somehow, where they wanted to know whether college students, women, whether college females, students had the same ideas about what their future lives were going to be like as their parents. So say a female student and her mother, or a female student and her father, one or the other, and they would compare things like, how many years do you believe that you will work full time after you graduate from college before you go into full retirement? Most students used to greatly underestimate this. They'd say something like 15 years. Most careers are 40 years long, at least, but the average is around 40. And they 15 years, and I go, oh, the poor things. They're going to be really pissed off in their late 30s, man. Parents, on the other hand, would say something closer to 40 years. Mothers, especially. Fathers, they didn't like that. Fathers wanted their daughters to be able to work as long as she wanted, with whatever she wanted. Anything she wants is great. She can do anything. But as soon as she has a kid, she stops working full time. She raises those kids through high school. And then if she wants to go back, that's fine. Tell that to anybody with a law degree. It just doesn't work. Right? So that's what their questions were, but they asked things all wrong. So I had to run a series of dependent t-tests to compare the scores between the students and their parents. But think about it this way. If I compared you with your mother, that's different than putting all your scores together and comparing that to everybody else's mothers, right? So we wanted to see if there was a difference between matched samples. So we had to keep track. Susie and her mother, Doris, had to be kept separate from Mary and her mother, Anne. And so you're matching the samples carefully. They're a paired sample. So usually it's when we have one sample and we're measuring them twice. But whenever we're in a situation where it's very important to keep the pair together, we also do this. The best example of it isn't the one I gave you. It's actually twin studies. Let's say that we want to know whether twins who were separated at birth, say by adoption, whether how they were raised changes their IQ. So we want to keep the two twins who were born together separate from those other two twins who were born together. We want to know whether specifically the pairs are different from each other, not the overall general means. Does that make sense? There's mathematical power, the ability to reject the null hypothesis, mathematical power, finding a difference if there is one, in doing this dependent t-test. But you have to have a reason to do it as a dependent t-test. And so you have to make sure that it's something where you're matching the samples. So there's power from doing a dependent t-test. There's also power from how we set our alpha level, and there's power from whether we use one or two tails. And there's power from how big of a sample we use. The more in the sample, the more mathematical power we have. It's just the way the formulas work. They all have n down there in the denominator. And the more power that you have, the more likely you can reject the null hypothesis and say that what you're doing actually made a difference. So there was a difference between the groups, or a difference between pre and post, like that. Difference between the generations, difference between the twins. Okay, that's a lot of philosophy. I think it's too much, to be honest, but you needed it before we can actually go on, because otherwise it's just like following a recipe and not knowing why. It's like, there's this stuff called yeast. I don't know why yeast gets put in recipes, but my mother always did it, so I'm going to do it. Like, now you know what the yeast does, but it'll be hard to remember. So I'm going to be refreshing briefly as we go along, trying not to get too far off topic. It's one reason why I covered degrees of freedom earlier. It's one reason why I'm covering the tails, one-tailed versus two-tailed earlier, because the way we state the alternate hypothesis actually changes the values that we're looking for in a t-table. And if we don't understand that there's different ways to state it, it's very confusing later. But there are different ways. You can state that it's different, or you can state the specific difference. Okay, so one more time, I want to talk about that. And I want to talk about two-tailed versus one-tailed briefly. Two-tailed is when you are predicting that there is a difference between the two means, a statistical significant difference between the two means, either direction. One-tailed is when you are predicting the specific direction of the difference. That one group will score lower than the other, or that group will score higher than the other. When you are predicting the direction and you get it right, good for you. But there are ways that you can really mess it up. You can predict the specific direction and get it entirely backwards, right? You could say, this group's going to be significantly higher than that group, and something goes crazy while you're doing your data collection, and it goes in the wrong direction. Happened to me with my master's thesis. I predicted that women would be more likely to pick up a certain piece of information from men than they would from other women, and I pictured the same about guys. But the women didn't do that. The women went to other women for this little piece of factoid, and I couldn't figure out why until I had to take a restroom break while I was collecting data. This was in an entryway to a college classroom building. And I went into the restroom, and there was a big sign as soon as you go in the room, on the door to the room on the outside, as soon as you go in the room, on the mirrors, every mirror, and also inside every stall. I checked because I needed to write about it in my thesis. The sign was about a recent rape that had taken place on that campus and how women should avoid men that they don't know. So the women who I predicted would go to get the thing from the mail because they would think men knew more about this topic. Nope. Nobody went to the guy. The other guys didn't want to be associated with somebody who's a guy that they didn't know because they didn't want to deal with a rapist. And the women didn't go because they're now terrified. Everybody was terrified. If I had been paying attention, I would have realized before I even started that everybody was talking about this. But it wasn't my school, so I wasn't paying attention. Okay, so that's called a boomerang effect. And my one-tailed hypothesis fell down and went boom. Just all wrong. And it was a master's thesis. So luckily, in a master's thesis, you don't have to break new ground. You just have to understand what the hell you did. And so I had to write at length about what went wrong and what I could have done differently. And then when they saw it, they're like, come up with more ideas about how it could have been better. So I paid my dues. So it matters. The direction that you predict matters. And when you're wrong in the wrong direction, you don't even really have to go any further. You're just wrong. But if you're in the right direction, you still have to see if the means are far enough apart. Okay, so that's two-tailed versus one-tailed. So what I'm going to do next is take us through the steps for first a one sample t-test, and then after that we'll go through the steps of how we do an independent t-test, and then after that a dependent t-test. There are online calculators for all this. There are online calculators for confidence intervals. I gave you a problem and I quickly went to a web page I know that does confidence intervals and put the numbers in so I could get the answer key. I made up the numbers, but I got an answer key out of it. And then somebody wanted me to look over something, I can't remember what it was, something about theirs before they handed it in. They weren't sure they were doing something right. And I looked and it was like, yep, you're right, because it matches the answer key that I already have. So there's t-test tables too. I mean, not just tables, there's t-test formulas. You put your numbers in, the group's mean and standard deviation, and what you want alpha to be, and it'll tell you if you have a significant difference between the means. But you're going to learn how to do it the hard way with the results and the data. We'll use summary statistics for most of it. This is the group's mean, this is the group's standard deviation. But once in a while, I'll probably have us do like you have a small group with their actual data, and you'll compute using your calculators, you'll compute the mean and standard deviation, because that's the way it works in the real world. And then eventually you're going to have two homework assignments. One's going to be to do an independent t-test when you have two groups, and you're going to pick a variable to test them on. And then you're going to run through all the steps of hypothesis testing and write it up, just like you would write it up if you were doing an experiment, but briefly. And then when we get to correlation, you're going to do the same thing all over again with correlation. You're going to collect data and then run that through. Okay, let me just start doing a little bit of this. What do we got, 15 minutes? Yeah, that's good. Okay, so I think what I'll do in this 15 minutes, rather than actually doing a problem, I'm going to give you the philosophy, not the philosophy, but the steps that we use. So I'm going to do, you know what? I'll do it with a problem because it'll make so much more sense. I usually do it the other way, but I think without being able to be right there and see who looks the most confused, because some of you actually are not sharing your screen. I can't quite tell who's following exactly. I'll use it with a real problem. It'll help you. Hold on, I'm sharing my screen. Here we go. Okay. So I'm going to do the steps, the hypothesis testing steps. The first thing that we do, and what you will receive from me for every problem that we have, is alpha. So I'm not going to ask you to decide what the best alpha is, because that makes my job really hard. I just need to know one set of answers so I can help you through the steps. If you're picking your own alpha level, it makes it impossible to do that. So we'll preset alpha. Since alpha is almost always going to be set at 95% in psychology experiments, almost always we're going to use 0.05 for alpha. So alpha, first step, equals, this one we're going to do at 0.05. So here's the thing. Here's the example. It's not a psychology example. It's much easier to understand than human behavior. Let's say that you just got hired on as a quality inspector for a sprocket company. You know what a sprocket is? It's like a gear. Think of on a bicycle where the chain goes, on that round thing with the little teeth. That's a sprocket. Okay, so you got a round thing with teeth. Some of those are just called gears. Others are called sprockets. You can always go Google image for sprocket. Okay, sprockets have diameters. This is a nice simple thing. You just take out a ruler and you measure. Okay, you are working for the Alpha Sprocket Company. Congratulations on your new job. And you need to find out if they're making sprockets to specifications. They've gotten a contract. They're supposed to be making sprockets that are 6.3 millimeters. Okay, so here's what we know. We know the population mean, which we write like a mu, equals 6.3 millimeters. That's like maybe 1.5 inches-ish. I think I got that right. No, I don't think I have that right. Anyway, 6.3 millimeters, whatever it is. Okay, so we have set up our sprocket making machine to make sprockets to that specification. And now we have to find out whether or not we've done a good enough job. Not every sprocket's going to be perfect because the machine can't be calibrated perfectly, right? But if they're close enough to use, then we should be okay. So next, what we're going to do is we're going to set our null hypothesis and then our alternate hypothesis. Our null hypothesis is that we're going to run a set of 25 sprockets, and our null hypothesis is that there will be no significant difference between our sprocket diameter and the population diameter. We know the population diameter. So one way to write this will be that our sprockets will be close to 6.3 millimeters, but the better way to write it is to say there's no significant difference between sample and population. Sprockets. Okay, no difference. Good enough to go run the machine. In this case, we like the null hypothesis. The alternate hypothesis, what you have to decide before anything else is how many tails do you want? Do you want to say it matters whether, do you want to predict that they're going to be bigger, or do you want to just say they might be bigger, they might be smaller? And that's a difference. And I think since we're just calibrating a brand new machine for this company, that we could be wrong in two directions. We could make them too small, or we could make them too large, right? Both ways would not be good. Both ways means we have to recalibrate the machine. So we're going to use a two-tailed hypothesis in this case. We need to remember that because we're going to have to look something up in a table that asks us about tails. Is our sprockets it could be in either direction. So let's just say won't be the same size. The next step after that, which we are not going to do now, is we are going to compute a score called a t-score because we're doing t-tests. And we're going to find t computed. And I'm going to stop there because I'm going to give you data and we're actually going to compute that number. And it doesn't make sense to tell you the other steps because it'll just sound like more jargon. I'm going to wait and do it with the example. So t computed. I'll even throw the mean in for now since I have another minute. The sample mean minus the population mean divided by that standard error, which means sample mean minus the population mean over the sample's standard deviation divided by the square root of n. And one last thing, notice that the denominator of the denominator is n. It's the square root of n, but it's the same thing. So it's n. The higher that number is, the higher the denominator in a denominator is, the larger the ultimate number will be. If this n is 30, we're going to get a larger t value, t comp for computed, than if this n was 10. It gives us more power. We're going to get a higher t computed value, which is good if we want to see a difference. In this case, it's actually bad because we don't want to see a difference. But the more n we have, the more we can reject the null hypothesis. Usually we want to. So that's why we always have big sample sizes. In this case, we want a decent sized sample because we don't want to have to get this wrong, ship it, and then lose the contract. We want to get it right. But it costs a lot of money to run it. These are titanium or something. So we're only going to probably end up with a sample of 25 or something like that. I think I have in my notes. So we'll get to that part on Wednesday. Okay. So this week on Wednesday, I'm going to finish showing you how to do t-tests. We'll do a bunch of examples. And then on Friday, I'll give you the day to do a one sample t quiz. Okay. So try